All right. Hello, guys. Welcome finally to the last section of chapter 15. So today we're going to be doing change of variables in multiple integrals. We have actually encountered this multiple times. So in a double integration, we know we change the Cartesian coordinate into polar coordinate, right? In triple integral, we change the Cartesian coordinate into either cylindrical coordinates or spherical coordinates. So those are special cases where if you're treating the domain with some symmetry, then you will be able to apply those type of transformation. But there should be a general theory on the change of variables, and that is what we are going to do today. So first of all, let me start with some sort of a motivational example to see how the change of variable works. And then we're going to introduce the actual change of variable formula and then provide a ton of examples. Okay, so first of all, this is one of the exercise in your textbook within this section. We want to evaluate the double integral of cosine y minus x divided by y plus x, where the integrating domain omega is given by the trapezoidal with these four vertices. I have actually drew it out here. So it is a trapezoidal with two of the sides being the axis and two of the parallel sides being something parallel to x plus y. This is x plus y equals to 1, and this is x plus y being 2. Okay, so you might see that this is a rather complicated function in terms of x and y, in the sense that we don't really know how to find its anti-differentiation. So the idea is quite simple. We want to make the numerator and the denominator to be a new variable, in the sense that if we are simply treating something like this, then we're able to evaluate its anti-differentiation with respect to u or v. So this is the basic idea. And you can see that this is exactly what I do. So I set u of v to be y plus x and y minus x respectively. So u is given by the denominator here, y plus x, whereas v is given by y minus x. And I denote this by t inverse xy. So basically, I'm saying that we translate uv to y plus x, y minus x via t, meaning t of uv is y plus x, y minus x. On the other hand, we have t inverse of xy being uv, which is y plus x, y minus x. I will explain this notation afterwards, but this is the notation that we fix on there. So you can actually calculate the inverse transformation, t of uv, meaning that we want to represent xy in terms of uv. So it boils down to solving this two guy. It boils to solving xy in terms of uv via these equations. U equals to y plus x and b equals to y minus x, which you can easily solve that x is equal to u minus v divided by 2, where y is equal to u plus v divided by 2. So after translation, we want to figure out what is the difference between the integrating domain. How is the trapezoidal change under this type of transformation? So we see, first of all, this line, the y-axis, is given by x equal to 0, right? In terms of uv, that is u minus v equals to 0, or simply u equals to v, right? That is this blue line. These two are correspondence. And what is y equals to 0? It is simply u plus v to be 0, and that is u equals to minus v. Lastly, this two slanted line, x plus y equals to 1 and x by y equals to 2, we see that x plus y is nothing but simply u, right? So you have u equals to 1 and u equals 2, which we draw it here. And a new vertices is given by, this is a new trapezoidal, where the vertices is given by this a prime, b prime, c prime, d prime. Then they are in one-to-one correspondence with the a, b, c, d here. So this is basically the transformation, how t translate the trapezoidal into another trapezoidal. And yeah, that's what we have now. So to evaluate the integration over omega cosine of y minus x divided by y plus x, we are in the position of translating y minus x to be v and y plus x to be u. Well, be careful. So whenever you're applying some type of change of variable, there's always three things to be careful to change. The first thing, obviously, is the integrand. That is the key idea of changing variable. We make the integrand into a nicer function. The second thing is the domain. So in this case, we actually want to integrate on a UV domain, which under my transformation here, we see that this T inverse omega carried by this function T inverse is another trapezoidal. Okay, so you have to change the domain. Thirdly, you have to change the so-called infinitesimal term. We'll justify this name by Jacobian afterwards, but that is basically how the area changes from under this transformation. So in this case, this kind of transformation is sort of a linear transformation. So the area is kind of a constant section, meaning that for every infinitesimal part, you actually have a constant change of area. It might be stretched by size 2 or shrink by size 1/3. So it is a constant section. This type of transformation does not, this kind of property is not a general property. So most of the transformation actually does not share that property. But in this case, we actually have a nice stretching because you can see that these two guys are actually similar in the sense that they're both trapezoidal, and that this transformation only stretches and shrinks things. So anyway, what we want to do is actually to find out the ratio between what we have, the area of, oh, I don't know why I write R. Let me replace this by omega. So I want to find out the original area to the ratio of the area of the new domain. In this case, T inverse omega. Pardon me. Okay. So yeah, as I mentioned, so these are the three things we want to change: integrand, the domain, and the so-called infinitesimal terms, which we will be calling Jacobian afterwards. So first of all, what is the area of omega here? It is a very simple trapezoidal. We can evaluate it using whatever formula you like. For example, uh, let's just maybe divide this by two triangles. Then you have 1 times 1 divided by 2, and 1 times 2 divided by 2. That is 3/2, right? That's the area for the omega. And for the area of the T inverse omega, it is another trapezoidal here, right? With the upper and lower base being 2, 4, and height being 1. So the area will be 2 plus 4, 2 plus 4 times 1 divided by 2, that is 3. And you might ask, why is the area of T inverse omega at the denominator instead of the numerator? So you can sort of treat this guy. Let me mention this. So this dA prime is respect to u and v, and this dA is respect to x and y, right? So this type of u and v thing cancels out with the area thing, and this thing becomes dxy, if that makes sense. So we're trying to create the integration with respect to u and v by introducing a extra term so that it makes sense that this is equal to this. The infinitesimal term in terms of x and y is equal to the infinitesimal term in terms of u and v, accompanied with a particular ratio of areas. And now then it is quite a simple calculation. So T inverse omega, this guy can be regarded as a type Y region. X can be fixed towards 1 and 2. U can be fixed towards 1 and 2, where V can be simply fixed towards minus U and U. So you have that guy. And so you see that everything becomes much more simpler in comparison to this integration. Because, for example, by integrating over V, you simply get U sine of V divided by U. Plugging in the corresponding points v equals to u and v equals to minus u, we actually get a constant, sine 1, where you're simply integrating u over this integral. And you get 3 over 2 sine 1 for this integration. As I mentioned, this is a very, very, very special case in the sense that the scaling of the area actually is uniform. The uniform is in the sense that every part of this trapezoidal actually scales the same under this transformation, like that. This does not hold generally, and we will obviously reduce the general formula. But this is, I hope this sort of provides an intuition on why we're doing this, because this is in general hard to treat. And the motivational kind of point is to replace the variable to make the function simpler. But we have to accommodate how that type of change of variable affects the integration. And there's twofold of impact. One is the domain, and one is this infinite epsilon term. Right? Okay, so now let us try to derive the general formula for the change of variable theorem. Pardon me again. Right. So now let us consider a one-to-one mapping. So one-to-one means that every UV is uniquely associated to XY, meaning that you basically, yeah, it's the definition of one-to-one. 1 point corresponds to 1 point, and there cannot be 2 points that match the same point. That will guarantee the uniqueness between the transformation, right? So as mentioned, we fix the notation to be UV equals to T inverse XY, or in the same way, XY is equal to T of UV. So be careful, this T here is actually a two-variable function with two components. So it sends UV towards XY, and T inverse sends XY towards UV, okay? There's two components. Okay, so this is the graph that we are trying to do. In general, we might have a strange tiny infinitesimal piece in the XY domain. So that is fix the notation here. First of all, again, we try to chop the UV domain into several small grids and want to integrate over those grids. So that made the notice by UI, Bj, UI plus 1, Bj, UI plus 1, Bj plus 1, and UI, Bj plus 1. As usual, the difference between Bj and Bj plus 1 is given by delta Bj, and the difference between UI plus 1 and UI is given by delta UI. So now, if we translate this into by T, XY domain, then we have, as mentioned before, the correspondence between A prime A, B prime B, and so on and so forth. We have T of UI Vj, T of UI Vj plus 1, and also the remaining 2 points. So this thing might not look like a rectangular. It might not even look like a trapezoidal or parallelogram. It looks like anything you might imagine. It might be a circle. However, when these guys are close enough, that means that these guys are close enough, provided T is a good function. We know whenever these 2 points are close, then these 2 values are close, right? So when the distance delta ui and delta vj are small enough, then the image after mapping T actually looks like a parallelogram, meaning that we can actually estimate this red area under this blue area, the area of a parallelogram. So now let us try to estimate this. This will be the difference, or the difference of the infinitesimal term between UV and XY. So let us denote this by A, the vector A, and this by the vector B. First of all, A is simply the vector given by, actually, this is a strict equality, my bad. A is a vector given by taking difference between T ui plus 1 Vj together with T ui Vj. So basically how this line translates under T. And so You can call this maybe mean-value theorem, but basically when ui plus 1 and ui are small are close enough, then you can estimate this by linear approximation, right? So let us recall this. Let me maybe use a one-dimensional version. We know that fy is equal to fx. Sorry, maybe let me use an approximation. It's approximately this guy, f prime, y minus x, right? This is called a linear approximation at the point x. So we're doing that in the first variable, u. We know that the f prime here is simply the partial differentiation with respect to u, right? I'm plugging the corresponding initial point x, which is ui, multiplying the difference between ui plus 1 and ui, which is delta ui. So the difference between t is close to the difference between u multiplied by the slope in terms of u. And same thing happens for b. So b is given by t of ui vj plus 1 minus t of ui vj. And that is again given by, wherever these two guys are close, the partial differentiation with respect to v times delta vj. So don't forget, this is a number, and these are actually vectors. Because tu, as I mentioned, t is a two-variable to component or to output function. So by differentiating with respect to u, I'm saying that we differentiate x by u and differentiate y by u. So this is actually a two-dimensional vector, okay? And that matches up with our intuition because this should be a two-dimensional vector. So why do we want A and B? Because the parallelogram can be computed, the area of the parallelogram, Rij, can be computed using the cross product between these two guys. And technically, there is no cross product in two-dimensional space, but we can regard this A and B by leaving in the three-dimensional space with the z coordinate being 0, right? That makes it into a 3D vector. And the area spanned by A0, B0 is the same as the area spanned by A and B. So now, by definition, we have I, J, K. So this should be approximate. It would be a better notation. We know that A looks like this. So, as I mentioned here, Tu ui vj is simply taking partial differentiation of x with respect to u, partial differentiation of y with respect to u, and plugging in the corresponding point, ui vj. Don't forget again, x and y itself are functions in terms of u and v. Okay, so you have partial x, partial u, plugging in the corresponding point times delta ui, and also partial y, partial u multiplied by the difference between ui plus 1 and u. The same thing happens for b, and now we can compute the determinant. The first two coordinates are 0, whereas the only surviving term, the last coordinate, the z coordinate, is given by this guy times this guy minus this guy times this guy. And every guy have a delta ui, delta vj. We can factor that out. And you're simply finding out the length of a vector with one component. So the only possible, it can be computed directly by just taking the absolute value of this, right? Okay. So what are we doing now? Well, what we have now is under the transformation T, we see that the original area delta ui, delta vj is now translated into something that is close to this strange thing, partial x, partial u, partial y, partial v, minus partial x, partial v, minus partial y, partial u, multiplied by the original area. This is called the Jacobian. It coincides with our previous term here, which we will see later. So let us give a formal definition. If T under some domain, D belongs to R2 is given by T of UV being X of UV, Y of UV, then the Jacobian of the transformation T is defined to be JTXY is a function, sorry, I should write JTUV to be more precise, because T is a function of U and V. So JTUV is given by this thing here. And sometimes we will write it in terms of this notation, partial XY, partial UV. So the numerator and denominator are fixed, okay? If we're dealing with the transformation from UV towards XY, then it's XY divided by UV. When it's the reverse way, then vice versa. So basically what we have in the previous discussion is that if we're trying to understand the Riemann sum in terms of the usual way, so this is the choice of points evaluated, the function evaluated as some choice of points multiplied by an infinitesimal area in terms of x and y, right? And we know that we can evaluate this guy by some t of ui vj. Maybe, let me mention this. Let me write t of ui star vj star to be more precise. It is some particular choice of points where we have compute this area in terms of u and v to be the Jacobian, taking absolute value. So don't forget this guy might be negative. Taking absolute value times the area, infinitesimal area in terms of u and v. So by this kind of computation, if we push the match towards zero, or simply saying n and m towards zero, we cut the grid to be self-fine, then this guy converges to the usual Riemannian integration over x and y. And this guy converges also to some Riemannian integration, but you now have extra term here. So you have f of t of uv together with jt of uv and delta u delta v. So again, let me mention there's three things to change. One is the integrand, one is the domain, and one is the Jacobian. And there's obviously some technical conditions. We might require that t should be 1 to 1 to make sure that it is each point are uniquely associated with another point. And we also require the Jacobian to not be zero for every UV consideration. And you won't really have to verify this condition. It won't appear in your quizzes or exams. And in most cases, this type of sick things will not happen. It only happens when your T is very, very strange. So yeah, what I'm trying to say is that in most cases in your textbook, in your exams, or in perhaps most of your academic career, I might say, this type of strange T will not appear. So you can just assume that this type of trainer variable is valid. The only thing that you have to be careful with is that T has to be 1 to 1, meaning that U and V and X and Y has to be 1 to 1 correspondence. So let me sort of compare this formula with the previous formula in the one-dimensional version. We know that in the one-dimensional form, if we're integrating f of x from a to b, then you can translate that by pushing back f of g of u multiplied by some g prime of u, and the lower and the upper integral boundary is given by g inverse a and g inverse b, right? Provided g obviously should be a 1-to-1 function. So the only difference actually between these two guys, you can see that it's actually in the Jacobian term. Here we don't put the absolute value, but why is that? So we see that whenever g prime of u is positive, then g is increasing, right? So g inverse is also increasing, meaning that this guy is larger than this guy. So everything here is positive. And also, when g prime of u is negative, that means g and g inverse are decreasing. Oh, decreasing. So that means that g inverse b is less than g inverse a. So you have something like 5 integrated over 3. So this is negative, and this obviously gives you an extra negative sign, so everything is still positive. So this g prime of u actually does not require any absolute value because it corrects the signature by itself. And this is called the orientation. And in a one-dimensional version, the orientation is quite simple. You either go from left to right or right to left, right? In a two-dimensional, even higher dimensional version of integration, it'll be a little bit hard to define the so-called orientation. That is why we always fixed the Jacobian to be positive. And also this integral is over some region which is non-oriented in somehow. It is simply a domain. We don't care about the direction in some sense that it provides. So this topic will become important in chapter 16, so we'll talk about that later. Orientation is actually a very important concept in integration, but it requires some notation to define what orientation means for a two or higher dimensional object, which we will discuss later. So this is the comparison between these two-dimensional chain variable formula with one-dimensional chain variable formula. And also to simplify notation, we observe that the determinant, you can recall this from section 12.4, AD minus BC can actually be used to evaluate Jacobian. We see that Jacobian JT, or usually we write it in partial xy, partial uv. I again use xy, and I may use uv here. It's given by partial x, partial u, partial y, partial v, minus partial x, partial v, partial y, partial v. And this can be written down in terms of this determinant. Note that the way we write this, the Jacobian matrix, is usually the first row corresponds to the same function. So you see that this is a function x, right? And the same column corresponds to the same variable. So this is the variable u, and this is the variable v. So you can sort of memorize Jacobian matrix by that. And we see that this is a sort of nice short abbreviation for our Jacobian thing instead of this thing, which is hard to memorize. Okay, so let us start doing examples. First of all, for our previous example here, we know that the transformation towards from u v to y plus x y minus x is given by t of uv to be u minus v divided by 2 and u plus v divided by 2, where the inverse transformation is given by y plus x and y minus x. So we see that this is what I just mentioned, and therefore transformation Jacobian partial xy partial uv is given by this guy. So you differentiate x by u, which is half, right? This is x of uv. If you partially differentiate by u, you get half. And the same thing happens for, say, this guy. Differentiate y respect to v gives you minus half, right? So my bad, this should be minus half. I seems to, wait, x is given by, oh, this is plus. Okay, so y differentiated by v is positive half. And I get a corresponding for guy, which you get half. Where does this half come from? So you see that it actually is the same with the difference, sorry, the quotient between areas, right? This is what I mentioned by a constant rate of change of areas. So this is a constant in terms of u and v. So every infinitesimal area in omega translate back to the area of T inverse omega with a same rate of change, in this case, half. Okay, now let us find the Jacobian of our usual transformation, the polar coordinate. So now we want to justify the formula we provided before in section 15.3, I think. So we know that we translate r theta by t to xy using this formula, right? R cosine theta, r sine theta. So the Jacobian of xy respect to r theta is given by differentiating x respect to r, x respect to y respect to r, x respect to theta, and y respect to theta. This guy simply gives you cosine, this guy gives you sine, and so on and so forth. You'll see that the determinant cosine times r cosine theta is r cosine squared minus sine theta multiplied by minus r sine theta, and that is r sine squared. This guy, by Pythagorean theorem, is 1. So you have r at the end of the day. And this actually coincides with our formula in the polar coordinate, right? I always emphasize that you have to add this extra r when you translate everything back to polar coordinate. Okay, let's do some abstract examples. So you're asked to evaluate this guy, sine of 9x squared plus 4y squared over the region omega given by some ellipse. So obviously, ellipse is a stretching of circle, right? So this should be not much harder than doing integration over circle. But we don't have a so-called ellipse coordinate, right? That is why a general version of the change of variable formula should be applicable. Let us try to make things into a so-called polar coordinate. Let me write x to be 1/3 of r sine cosine theta, and y to be r over 2 sine theta. The motivation of doing this is very simple. We want this guy to be cosine squared and this guy to be sine squared. and then you simply have this guy, right? Okay, so in terms of R and theta, you simply have zero from R goes from 0 to 1, and theta goes from 0 to power 2. Okay, we require first quadrant, so 0 to power 2. So now let us evaluate three things to mention. One is the integrand, one is the domain, and one is the Jacobian. So first of all, the integrand, 9x squared plus 4y squared simply gives us r squared. You have sine of r squared, where r goes from 0 to 1, theta goes from 0 to power 2, and Jacobian of x, y respect to r theta. So let me remark here that you can see the convenience of this type of notation. It actually tells us that you have sort of a nice cancellation in some sense that this is cancelled out with this guy to be dx dy, right? So the original dx dy is equal to partial, dx dy is given to be partial xy, partial r theta, dr d theta. That sort of makes sense, right? Because this two guy cancels out in somehow. Okay, and don't forget the absolute value between the Jacobi. So maybe a second remark here. This thing here is a determinant, right? Determinant may be negative or positive. So this extra absolute value here is to make sure it is positive. As I mentioned before, we really don't care about orientation for now. We'll introduce that minus signature afterwards. But for now, we can simply differentiate x with respect to r and theta, and you get this Jacobian matrix. Taking determinant, you get 1/6 r, which is not really a surprise because r is the original Jacobian of polar coordinate, right? This 1/6 simply comes from the structure of this and this. 2 times 3 is 6, right? So you can move this 1/6 to the front, and this extra r provides you a nice change of variable to make this and then have differentiation given by minus half cosine r squared. Plugging in the corresponding boundary, you get some value power 24, 1 minus cosine. So you can see that this is actually really nice in a sense that we can work out things which does not obey the usual, say, polar coordinate transformation or cylindrical spherical coordinate transformation. You can have a very big flexibility on the coordinate that you choose. I want to mention here that this is, in some sense, kind of different from polar coordinate. So the theta here actually does not has the usual geometric meaning. So don't forget when we're dealing with the polar coordinate, the theta is simply this angle, right? This will be, say, r cosine r sine. However, this thing does not obey the same rule in this sort of ellipse coordinate. So if, say, this point is given by r/3 cosine theta and r/2 sine theta, then this angle is not theta in general. It is only a coincidence that this particular point gives you theta being 0, and this particular point gives you theta being pi/2. But in general, for every point here, this angle is not the angle here. This theta is simply a so-called parameterized agent, which we will talk about it in section 16. This does not, for now, has any geometrical meaning here. This angle is not the parameter theta, okay? Okay, so let us provide a second example, which has nothing to do with the polar coordinate. We're integrating over the function x and y, x times y, over the set omega, bounded by these two hyperbolas and these two lines. If you draw it out, this is 1 over y equals to 1 over x. This is y equals to 4 over x. And you have two lines, which looks like a cone, y equals to x, and then y equals to 3x. So the omega here is what we want. So to make life easier, the motivation is to make this a coordinate curve, coordinate line, meaning that you should be thinking this as xy being 1. So by setting xy to be u, you had u equals to 1, right? So the hardest part, actually, I would say the most complicated part about this chapter or this section is to choose the correct u and v to make life easier. It is, in general, there's no general method to choose that. There's no algorithm. So it's solely based on experience and how you would like to treat your integral. In this case, my motivation is to make life easier, to make this a straight line. So for example, this becomes u equals to 1 and u equals to 4, right? And if we set the quotient between y and x to be v, then this is simply v equals to 3 and v equals to 1, right? So you see that is why I choose u and v to be these two guys. Obviously, you have to plug that back and to see if actually things actually work. I obviously have already done this problem, so yeah, this type of general variable works. So you see that our original domain given by y xy, where xy is bounded between 1 and 4, and y over x is bounded between 1 and 3, can be translated by u and v, where u is between 1 and 4, and v is between 1 and 3. So we have to now evaluate the Jacobian, right? We now know that T inverse of x and y is given by xy y over x. We have to evaluate what is T of uv, right? Basically, we're saying that how can you solve x and y in terms of uv via these two equations? And it's quite simple. For example, how do we solve for x? X is simply this guy divided by this guy, taking the square root, right? So uv given by xy and y over x can be translated to x given by u divided by v, taking square root, y given by square root of uv. This is what we call a one-to-one correspondence. Given a fixed uv, you have a fixed xy, and vice versa. So the mapping that we're considering is T of uv being square root of u over v and square root of uv. So we see that the Jacobian is given by this matrix. The partial derivative of x respect to u is given by half times 1 divided by square root of uv. The partial derivative of y towards u is given by half times v divided by u, taking square roots. And you can perform the same thing here. This will be partial x, partial v. This will be partial y, partial v, for all of them. And if you do the determinant, you can get a very nice Jacobian 1 over 2. So we have everything now in mind. The integration of xy over omega can be evaluated by this thing. First, change the integrand. Xy is simply u, right? And then add the Jacobian. So 1 over 2v. Don't forget your absolute value. And then you have the boundary, 1 to 3 and 1 to 4, right? U goes from 1 to 4 and v goes from 1 to 3. And so you see that life becomes very, very nice because this is actually separable. You can put you can integrate u and v separately, and you get this particular number, 15 over 4, ln 3. So this is a very classical example of general variable. You see that originally you're integrating for a not that symmetric function over a not that symmetric region. But after pulling everything back into a rectangular thing, things becomes very nice. So again, this is the hardest step. Everything after that is just straightforward calculus and computation. Okay, now let us discuss the 3D change of variable. It is the same as 2D, and the only thing different is that Jacobian becomes a little bit larger. Instead of a 2-variable 2-output function, now we have a 3-variable and 3-output function, x, y, z to u and u, v, w. So again, we require some technical conditions, which is like 1-to-1. The function maps u and v and w towards a unique point x and y and z, where the Jacobian is also assumed to be non-zero. The Jacobian here is obviously given by the same format. You have the function in the same row, same variable in the same column, and this will be a 3x3 determinant. Okay. So you can see that usually we're dealing with only this, but now we have an extra layer of output and variable. Okay. So the formula is exactly the same. We have the integral, the triple integral over f over the domain E is given by the integral of f plugging in the transformation T of u v w, multiplying the Jacobian, usually given in this notation, partial xyz divided by partial ubw over the region T inverse E. Okay, so let us provide some example. This is a not really a useful formula. You have to do that in example. So first of all, let us again try to verify what we have done in the previous lecture, which is that the spherical coordinate has a certain rate of change given by rho square sine theta, right? So don't forget the transformation between rho theta phi and xyz is given by x being rho sine phi cosine theta, rho sine phi sine theta, and rho cosine theta. And now evaluate the partial differentiation. The Jacobian of xyz over rho theta v is given by this whole big thing. So again, the same column corresponds to the same variable, the same row corresponds to the same function. And if you actually do the differentiation, which I highly recommend you guys to do this yourself, you get sine phi cosine theta, sine phi sine theta, cosine phi, and so on and so forth. To evaluate a 3 by 3 determinant, we have mentioned this in the cross product section. I think it's 12.4 or something. You do a so-called row expansion, right? In this case, I expand it with respect to the first row. So this guy times the determinant of this 2 by 2 matrix. This guy times the determinant of this 2 by 2 matrix with an additional minus sign. And this guy times the determinant of this matrix, which you have here. And if you do the algebra very carefully, you can get minus rho squared sine cubed cosine squared. And this middle guy gives you minus rho squared sine phi sine squared theta, sine squared phi, which is here, and cosine squared phi, which is here. Last term is simply rho squared sine squared phi, cosine squared phi, and cosine squared theta. So this is 1, right, by Pythagorean theorem again. And then you can see that if we combine this guy and this guy, you will get minus rho squared sine sine phi, sorry, sine phi. Wait, what I'm writing here. It's a little bit messy. Let me make sure I'm doing this correctly. Oh, yeah. There's an actual sign script here. That's why it looks weird. So this guy and this guy, let me write it down smoothly. Sine phi cubed cosine squared theta minus rho squared sine phi cosine squared phi cosine squared theta. You can obviously factor out the common terms, which is this two guy. And then you have sine squared phi plus cosine squared phi, which again gives you 1. And you see that this guy, together with this guy, we can apply the Pythagorean theorem again with respect to theta, and gives us minus rho squared sine phi, right? This actually coincided with our previous commutation. So if we take absolute value, what we have is simply rho squared sine phi. Don't forget that phi is within 0 and pi, so sine phi is always positive. And just to mention, the negative sign here actually has a meaning. That means that this orientation inverted the orientation of x, y, and z, meaning that the direction in terms of x, y, and z, if that can be defined, is the opposite to the direction of rho theta b in some sense. But for now, as I mentioned, we don't care about orientation, so you always take absolute value between your Jacobian, which you get now, rho squared sine phi, that coincides with our formula in section 15.8. You might note that I didn't do central coordinate because it is basically the same as the Jacobian of the polar coordinate. It's exactly the same thing. So for our next example, let us do a triple integral with something variable. So I want to evaluate the absolute value of x times y times z over this ellipsoid. X squared divided by a squared plus y squared divided by b squared plus z squared divided by c squared, that's equal to 1. Pardon me. Okay, So yeah, let us do this. First of all, we know that the absolute value is kind of a pain. So let us try to apply a symmetry. This guy is symmetric with respect to the origin, right? So we can simply remove the absolute value and evaluate everything in the first octant and multiply it by 8, right? This is what I tried to say. This guy. We only evaluate everything in the first octant and we multiply things by 8 because there's 8 different possibilities of x and y and z signatures, right? Now, this looks much like a ball, right? It is a stretching of a ball. So I want to make this to be u, v, and w. Then we can see x and y and z are given by au, bv, and cz, where the Jacobian now can be given by partial x, partial u, that is a, partial y, partial u, that is 0, partial z, partial u, that is 0. So this is CW. So you see that only the diagonal term remains, and the Jacobian is a times b times c. So the integral is now given by replacing first the variables. X is AU, Y is BV, Z is CW. The Jacobian, ABC, and the region of integration. First of all, it is this intersecting with the first octant. Now it is U squared plus V squared plus W squared less or equal to 1, but each of those guys are positive, right? Not negative, to be precise. And now you see that this is a very symmetric region in terms of the origin, right? You can apply spherical coordinates. So we see that UVW is rho sine cosine theta, rho sine phi sine theta, and rho cosine phi. Don't forget your extra Jacobian, rho square sine phi, and d rho d phi d theta. The ABC is constant, so you can put it in front of here, a squared, b squared, c squared, where you have radius going from 0 to 1, and v going from 0 to pi over 2. This is due to the fact that we only consider the z-axis towards the xy plane because we're dealing with the first octant, right? And theta also goes only from 0 to pi over 2. And then this very simple integration. Everything is kind of separable. Rho can be evaluated, v can be evaluated, theta can be evaluated. And at the end of the day, you simply get 1/6 a squared, b squared, c squared. So this is a nice example. In general, it would be very hard to deploy trainer variable in 3D space because you, in general, have no idea what is better to do. What is better to do. So, due to the nature of this chapter, when you're doing a quiz or you're doing the exams, in most cases, I figure I would give you the actual trainer variable. For example, I would tell you to say, evaluate this. Where is it? Here. I will say, please evaluate this integration over this region using this chain variable. I will give you that chain variable to be precise. Yeah, so that's all for this lecture. Let us go through what we have done. So basically, you only have to memorize this 2D chain variable formula, which is a lot similar to what we have done in the one-dimensional thing. But the only difference is that Jacobian now, the so-called infinitesimal change, is actually fixed to be positive for now. And whenever you're dealing with the general variable, you always have to change 3 things. One is the integrand, one is the Jacobian, and one is the domain. Okay? And Jacobian is defined as using the determinant, something like this. When you're dealing with a 2D term, something like this, when you're dealing with a 3D term. Okay? So yeah, again, for integration, I would highly recommend you do more exercise in your textbook. I have provided hopefully sufficiently motivational example for you guys to follow. And I will end the lecture here. I will see you in the next video, which is the midterm 2 review. And we can start to the most important chapter in a semester, chapter 16, which deals with the interplay between differentiation and integration. Okay, I will see you then.